Hi everyone, I'm Meriç and welcome to my channel. Today, here comes another topic, which is crack growth analysis. So, as you know from my videos, I don't like to just apply the analysis by using software. I like to teach the theory behind the analysis as much as I know. Therefore, there will be an introduction part of the topic and then we can continue with the ANSYS. So, let's start with what is crack growth analysis. According to the theory, first of all, there should be a predefined crack, and then we can have an analysis of this crack. The main point of this analysis is to see if the crack will be growth or not, and also we can see the direction of the crack growth by using this analysis. So, crack growth is very important, as you understand from the pictures. It can be seen any of the structural components which is subjected to a dynamic loading, and there is an example of the crack growth which is probably a fatigue failure, and there is a stress concentrator which is here. It can be an initial crack or maybe a notch, we don't know that, and then crack is growth at this direction. It is really good to predict the crack growth direction and the crack growth. So first of all, there should be a crack, and after that this crack will be propagated, and at the final there will be a phase fracture. So what causes crack initiation? This is the question. So it can be initial crack, or maybe it can be micro defects. Every material has micro cracks and defects. Maybe there are hundreds of them, maybe thousands of them. We don't know that. And also motion of the slip bands can be the cause of the crack initiation. When the slip bands move, there will be extrusion and intrusion, and these will be act like stress concentrators. So crack initiation, so that means crack initiation will be expected in every cases, in every structure. So here, this is our object, crack propagation. Flows, also known as cracks, they are stress concentrators. You can see it here. This is the crack tip and stress is higher here. This crack tip causes singularity in the body, and that causes the stress concentration here. So there's another example. This is an elliptical crack located at the body, and this is a circular one. As you know, the stress field is changed according to this hole and the circular hole. So that area will be a stress concentration area in that case, as you can see it here. So there are different type of crack modes. One of them is mode 1, which is opening mode. We will consider this case. And there is a mode 2, which is shearing mode. It's like a shear force. And mode 3 is tearing. I'm not going to get into the details of this topic because that will be a topic of my another video. So there are two options for the smart crack growth. One of them is fatigue crack growth. The other one is static crack growth. In the fatigue one, it uses Paris-Erdogan law to evaluate the crack growth, and which uses the alternation of the stress intensity factor. And by the way, according to this theory, crack growth is driven by the stress intensity factor. So let's continue. Static crack growth uses fracture toughness to evaluate crack growth, and there is a formulation of the fracture toughness or stress intensity factor. So in the static crack growth, rule is given here. Crack starts to grow if stress intensity factor of mode 1 is equal to fracture toughness or cracks start to grow when stress intensity factor of mode 1 is greater than the fracture toughness. Fracture toughness is also known as critical stress intensity factor. Also we can use J integral, and this is the same for it. J integral of the mode 1 should be equal or greater than the critical J integral, and when this happens, cracks start to grow. This is the case. So we need to learn the assumptions and the limitations of the smart crack growth because they are really important, especially the red ones. Smart supports 3D crack growth only, so we need to have solid body instead of 2D body. Smart crack growth supports mode 1 crack growth only, but I believe that at the feature that supports the mixed mode fracture. I hope that. Smart can be used with higher order tetrahedron mesh only, so that means we need to use quadratic tetrahedron elements in the body. Material behavior should be linear elastic isotropic. And also plasticity effects, nonlinear geometry effects, and crack tip closure effects are not considered in the analysis. In the analysis, we need to use either stress intensity factor approach or J integral approach. We cannot compete both of them in the analysis. These are the rules. So to make it more understandable, there is a picture. 3D mode 1 dominant crack growth. Mode 1 should be dominant in that case. And also material should be linear elastic. Here's the quadratic tetrahedral element, which is solid 187 in ANSYS. So we are going to define semi-elliptical crack in our analysis by using fracture tool. And there are a lot of properties that we can arrange. One of them is mesh counters. If it is 6, that means there are 6 circles around this point. And also, if it is 12, that means there are 12 circles around that point. So let's make it more understandable. Mesh counters is here. By the way, this picture is directly taken from the ANSYS website. If mesh counters is 3, that means there are 3 circles around here. And also, if crack front divisions is 12, that means this red line is divided by 11. If circumferential divisions is 16, that means all of the circles around here, all of them, is divided by 15, like here. And this is fracture affected zone, this height. This is the fracture affected zone again. So let's continue. So there is a good visual which is prepared by fracture analytics. In that case, yielding is not accounted. And also, as we already told, ignoring of crack shielding effects. And also, units of the stress intensity factor is different than we expected. In our case, that will be megapascal times root of the millimeter. That will be in our case. I hope that picture is meaningful for you. So let's continue with the material properties and the geometry. We are going to use structural steel, and we only need 2 properties. One of them is elastic modulus, the other one is Poisson's ratio. And also we need to define the fracture toughness to decide crack growth. Our length is 40 mm, our height is 10 mm, the thickness is 0.5 mm to reduce the computational time. I choose the thin plate but that will be a solid body. And also our properties is given here for the semi-elliptical crack. We are going to change these properties, and also we can change the buffer zone by using this one, but we are not going to change it. So let's continue with the ANSYS part. Let's carry the static structure into the system and let's change the material properties. So they are same, and we don't need this one, we don't need this one. They can stay, but we don't need. We don't need all of them. So we have only just Young's modulus and Poisson's ratio, and then we can go to the geometry and let's draw the rectangle. So click on the XY plane and click on New Sketch. So if we take a look at, let's change the unit as millimeter to make it easier. So we are going to sketch a rectangle. Let's go to the dimensions and click on the general. That will be 40, that will be 10 millimeter, and let's use extrude to make it solid body as a 0.5 millimeter thick, and click on generate. So this is the solid body, and we can continue with the model. So right click on the model and click on update. So the model is opened, and first of all, let's define the coordinate system for the crack, and then we can continue with the crack. So click on the coordinate system. That crack will be located at the middle of the body, and therefore coordinate system should be located at the middle of the body. And click on the geometry and click on the body and click on apply. This is already located at the middle of the body. You can arrange according to your case. And also, if you remember that coordinate system should be located here. X is at that direction, Y is that direction. So I need to change the X by using coordinate systems and the rotation of Y, because that should be rotated by using Y. So if you enter 90 degrees, that will be enough, and go to the model and right click, insert fracture. So in that case, we are going to create semi-elliptical crack. Click on the geometry and click this body. Change the coordinate system as a new coordinate system, which is here. So major radius will be 0.4 and minor one will be 0.2. The largest one will be 0.25, and mesh will be changed as tetrahedrons. But in that case, we will apply load in that surface. So to make it mod 1 dominant, I need to change the orientation of the crack. Go to the coordinate system and click on rotate X, and OK. And right now go to the fracture and generate all cracks. So crack is changed at that direction, and now mod 1 is dominant, but crack is not defined because we didn't change the mesh. So we need to insert method and click on the geometry and choose this plate, and method will be tetrahedrons and element order should be quadratic. We can arrange the mesh size as 1 millimeter. So let's go to the fracture again, and we need to generate crack. So crack is generated here, as you see that, but there is still problem. There is still one problem. In the smart crack growth, we need to open the crack nodes, crack face nodes. So therefore, let's open it and regenerate the cracks. Because as you remember that face nodes should be opened. So you can see the front and the face node here, and crack is generated here. And let's define fixed support and tensile pressure. So let's apply the fixed support here, and let's have a pressure, and direction will be X, and let's apply 10 megapascal. And so before we get into this solution, let's insert the crack growth module. But at the beginning I will suppress the smart crack growth, because at the beginning I want to see the stress intensity factors of this crack. So let's insert fracture tool, and let's select the semi-elliptical crack, and let's see all of the stress intensity factors, and also let's see we cannot see that yet, but we will see. Go to the analysis settings, and we cannot solve both stress intensity factors and J integral in the smart crack growth. Therefore I will close it at the beginning, and we will have a time stepping to capture the crack growth, and let's make it 5 to reduce the computational time, but we will see the more accurate results. I have already solved all of them. So let's solve it and see the stress intensity factor of this crack. So it is solved, and let's check the stress intensity factors. But let's remember the theory. If one of the stress intensity factors is equal or greater than the fracture toughness, crack starts to grow. And according to my case, I've already said it, that will be mode 1 dominant. Let's check it. Mode 3, stress intensity factor is less than the mode 1. And let's check the mode 2. And stress intensity factor is still little. And let's check the mode 1. This is the greatest one, and the maximum value is nearly 7. So the question is, what if my material's fracture toughness is greater than the 7? So let's unsuppress the smart crack growth, and let's define the initial crack as a semi-elliptical crack. And our crack growth option will be static, and let's say fracture toughness is 8. So let's see if the crack will be growth or not, and right click on the fracture tool and insert the crack extension probe, and that will show us how much millimeter this crack is extended. So let's solve it. So guys, it is solved, and let's check the crack extension probe, and we can see that crack extension is 0. As you imagine that in every substep, crack tries to grow, but fracture toughness is bigger than the stress intensity factor, so it didn't grow. So let's change the fracture toughness, which is smaller than the stress intensity factor, and let's solve it. But I'm not gonna solve it because the computational time is very high. So let's open the solved one, and this is 3 here. And let's check the crack extension probe. So you can see the crack extension here. Crack is extended at that time, and mesh is changed according to the crack propagation. So okay. So the main point is at the 0.6, at the time 0.6, it tries to grow. So let's go to the stress intensity factor, and let's change the display time as a 0.6, and let's observe the stress intensity factor at that time. At the time 0.6, this stress intensity factor is bigger than the fracture toughness. This is 4 and this is 3. So let's go back to time 0.4, or let's do it with another substep number. There's a 50 substep case, and fracture toughness is still the same, 3, but there are 50 substeps. And let's check the crack extension probe. The results will be more accurate. We can understand it more clearly. And we can see that after the point 0.4, crack starts to grow. Let's go to the stress intensity factor, and let's change the display time as 0.4. So let's see the result. It takes time because there are 50 substeps and the computational time is really high. So you need to see the 200 substeps. That will be more. So at the time 0.4, as you remember, crack has not grown yet. At 0.4, the stress intensity factor is 2.97. So let's go to the time 0.44 or maybe 45. Sometimes it cannot capture. So let's wait to solve it, and so we can observe that stress intensity factor is greater than the 3. That's why after that point, crack starts to grow. So let's go back to the crack extension probe and see how much this crack is extended. After the 50 substeps, crack is extended 0.6 millimeter. And let's see the 100 substep case, and let's go to the crack extension probe. Okay, and let's see how much this crack is extended. This is 1.25. This is 2 times greater than the 50 substeps. In every substep, crack is extended as the same value. You can see it here. In every substep, it grows as 0.03 millimeter in every substeps. If you, as a default, crack extension is related with the mesh size. So if you give the crack more time, that will grow more. So let's check the 200 substeps and see how much is extended. I think that will be 2 times greater than the 100 substeps. And let's check it. So it takes time. Yeah, crack is extended more. But we will have a comment at the end of the solution. Okay, at the 200 substeps, crack growth is 2.5 millimeter, and this is 2 times greater than the 100 substeps. So don't take it so much seriously. Don't take it so much serious. Just focus on the crack growth. According to this analysis, you need to consider that if the stress intensity factor is exist, then crack starts to grow. This is the main point here. And the other point, it takes time because this is really big. There are 200 substeps. And the second important point is crack grows at that direction. So probably we will see that after a short time. So it is a bigger crack because there are 200 substeps. So by the way, we can arrange the crack growth rates, but don't take it so seriously. So crack is growth at that direction because this is mode 1 loading, and in the mode 1 loading, I will show you, it's a little bit slow. In the mode 1 loading, if crack is here and the loading is here, crack growth should be the perpendicular to the applied load. So that's why that should be growth at that direction. This is the second main point, and this is the result of our analysis. So thank you for watching. If you like my videos, please like it and subscribe to my channel. Have a nice day.